Novatech Media.
A ray of light always escapes from us at the same speed, even if we try to catch up with it by approaching the speed of light.
But how is this possible? To answer this question, we need to understand what is light and what are we. All of us, even the grumpiest old men, were once carefree children. Swings were one of the favorite and sometimes the only amusement for many. But what do we see on the screen? It is a pendulum. And no matter how hard this smiling girl swings, one thing in this system always remains constant. It is the period of time that it takes for the pendulum to complete a full cycle. And this time depends only on two characteristics: the length of the pendulum and the force of gravity of the Earth. The longer the pendulum, the slower it swings. And the stronger the gravity, the faster. And if the force of gravity is constant, as for example on the surface of our planet, then the time it takes for the pendulum to make one oscillatory cycle will always be the same, regardless of how hard it swings. Now let's see, what will happen if we turn off gravity and replace it with a spring? If we choose the right spring and neglect the friction force, then the picture will remain unchanged. In this case, the force that will bring the pendulum back is determined by the elasticity of the spring. The stiffer the spring, the faster the pendulum swings, as if it were on a planet with stronger gravity. And the softer the spring, the less frequent the oscillations. Now let's complicate the system a bit and add another spring and a weight between the spring and the pendulum. Releasing the pendulum, the tension force of the lower spring will try to return the weight to its original position. The inertia of the weight will resist this. This movement will stretch the upper spring, and it in turn will deflect the pendulum in the opposite direction, starting a cycle of oscillatory movements of the pendulum. It may seem now that the oscillations of such a system are chaotic, but in fact, this is not the case. In reality, all the movements of the system repeat, and it always takes the same time. And now it depends not only on the length of the pendulum and the elasticity of the lower spring, but also on the weight of the load and the elasticity of the spring connecting the pendulum and the load, or, in other words, on the properties of the connection between them. Now, let's increase the number of links in our system. By deflecting the pendulum, we bring the system out of equilibrium and increase its energy. The energy we transferred begins to move through the system from weight to weight. But thanks to the fact that the length of the system has increased, the movement of energy through it this time looks more orderly and begins to acquire a familiar form to us. It is the wave. Starting its movement from one fixed edge of the system, it reaches the second edge, reflects from it, and returns to the beginning of its path. After that, the movement of the wave, or in other words, the movement of energy through the system, repeats. Now, let's get rid of the pendulum and the fixed spring. From this moment on, we can create waves of energy ourselves, moving through the system. The slower we move the weight, the longer the waves become. And the faster, the shorter they are. By deflecting the weights harder, we create waves of greater amplitude, and by making the movements less sweeping, we get low amplitude waves. But no matter how different these waves are in their length or amplitude, one of their characteristics remains unchanged. If all the weights and springs are the same, that is, the medium in which the waves propagate is homogeneous, then the speed of movement of any type of waves in such a system will always be constant. And this is true not only for a one-dimensional connection, but also for a plane, and for a volume, and moreover, for any number of interconnected dimensions, including the four-dimensional space-time, or in other words, the space-time continuum.
There is nothing that is smaller, and nothing that is shorter, than a quantum of space-time. Width, height, length, time.
Electromagnetic radiation is waves that propagate between quanta of space-time. Originally, the space-time continuum is a homogeneous medium, so energy propagates in it at a constant speed equal to 299,792,000 meters per second. This number is familiar to all of us as the speed of light. Similarly, as in the example with weights and springs, waves that propagate through the space-time continuum can have any amplitude and any length. Starting from the longest ones that we use for transmitting radio signals and ending with the shortest ones called gamma radiation. Among these waves, there is a small number of them that can be detected by our senses, more precisely by our eyes. We call such electromagnetic waves light. The greater the amplitude of the wave, the greater its energy. For example, if we are talking about the light range, then waves of the same length, but different amplitudes, or in other words, different energies, will look brighter and dimmer. But what will happen if both of these waves move in one dimension? Such waves do not create parallel dimensions, but merge into a third wave, which is the sum of the two original waves. This process is called interference. And according to this principle, not only two waves can be summed up, but also 3 and 4, and in the end, as many waves as you want, even thousands and millions. This rule is true not only for waves that move in one dimension, but also for waves that move in different dimensions. When combining a multitude of diverse waves, in some places they will repeatedly amplify each other, forming regions of space-time with very large amplitude, or in other words, with very high energy. The higher the amplitude of such a formation, the more it stretches the area of the space-time continuum around itself, making it inhomogeneous. This leads to the fact that waves that fall into this area pass a longer path and therefore slow down more, the more space-time is stretched along their trajectory. Here we encounter a new phenomenon. We face mass, and regions of space-time that have mass are called particles. Just as the interference of the same waves creates the same resultant waves, the interaction of the same resultant waves creates the same particles. And the interaction, or in other words, the interference of such particles with other particles in statistically significant scales, always gives the same results. This allows us to group particles with similar properties into groups. For example, into the well-known to us protons, electrons, and neutrons. But if mass is defined as the stretching of space-time, then will this section of the resultant wave have mass? The answer is yes, and it can also be considered a particle. This is the photon. But unlike the particles considered earlier, photons always move at the speed of light and have properties of both, and particles and waves, because in essence, a photon is just a high amplitude section of a wave. And if desired, any wave can be viewed as a stream of photons, just as conversely, any stream of photons can be viewed as a wave. Next, to avoid confusion, when talking about particles, we will mean only particles of the first type, which arise at the points of intersections of waves, and we will call particles of the second type photons. An individual particle is constantly changing its state, and depending on this, the waves that pass through it, with a certain probability, will slow down differently. Sometimes not slowing down at all. But the larger the number of particles on the path of the wave, the less value the probability has on its slowing down, and the greater the statistical reliability. A single wave, hitting an area stretched by mass, would only slow down its movement. But in space-time, waves do not exist by themselves. Waves are in 2 dimensions, but space-time in 4. A ray is a stream of energy that can be represented as parallel electromagnetic waves. Since the waves move at the same speed, the ray is stable not only in the direction of its movement, but also in all other dimensions. When a ray hits an area stretched by mass, the waves closer to the center of mass start to slow down. Where the waves move faster, there is more energy, and the energy of the waves that slowed down stayed behind. In this state, the system is not in equilibrium, and this leads to the emergence of a new wave, directed towards the center of mass. This wave exists until the energy reaches the most balanced state, that is, the one in which it was in the original ray. Leaving the area stretched by mass, the energy state of the ray remained unchanged. The only thing that changed was the direction of energy movement.
Hitting an area of space-time stretched by mass, any energy structure, whether it is a ray, a photon, or a particle, will deviate towards the center of mass, preserving all its other characteristics.
This phenomenon has a name: gravity. Every particle has mass. Where there is mass, there is gravity. The gravities of particles affect each other. Because of this, a tendency is created in which particles concentrate on relatively small areas of space-time. Such clusters of particles are called material objects, and regions of space-time saturated with particles are called matter. Material objects obey the same laws as the particles they are made of. And if the objects are massive enough, the result of their interaction can be the formation of waves with such a large amplitude that they distort space and time on a truly cosmic scale. We call these waves gravitational.